introduce myself. My name is Rima, and I would like to say welcome to our speaker today, Mr. Muhammad Aziz Majidi, Ph.D. Thank you for joining us, Dr. Aziz.
Thank you.
And also welcome to Professor Hussein Alatas as the head of Theoretical Physics Division in the IPB University. Also to all the faculty members and the students, the participants from the physics department IPB University, and all of you who are joining us today. I would like to say that I'm very glad to meet all of you, although it's in the virtual room. And I sincerely hope that you have excellent health. Okay, ladies and gentlemen, the IPB Physics Talk is a bi-weekly public lecture organized by the Department of Physics, Faculty of Mathematics and Natural Sciences, IPB University. And today is the very first event of a series, so please stay tuned for our next lecture. And today, our topic is about unconventional plasmons, concepts, and possible application. Will be delivered by Dr. Aziz. And before we begin, I would like to read a short resume of our speaker. Dr. Aziz Majidi is an associate professor in the Department of Physics, Faculty of Mathematics and Natural Sciences, Universitas Indonesia. And currently, he is the head of Physics Graduate Program. He obtained his BS and Master's degree in Physics in Universitas Indonesia. Also graduated from Diploma Program in Condensed Matter Physics from the International Center for Theoretical Physics in Italy. Dr. Aziz also obtained his Ph.D. in Theoretical and Computational Matter in University of Cincinnati, and dedicated his research at Oak Ridge National Laboratory, Tennessee, as part of his Ph.D. Also, postdoctoral research associate at the Department of Physics, University of North Dakota. Also visiting scientists at the National University of Singapore. And currently, Dr. Aziz is a member of several professional organizations. For example, Indonesian Physical Society, Indonesian Theoretical Physics Group, Material Research Society of Indonesia, and also Indonesian Magnetic Society. So without further ado, let's begin the main agenda for the day. And to all the participants, I would like to remind you, please turn off the microphone and keep your questions for the allocated time later. Dr. Aziz, time is yours.
Thank you very much, Mrs. Rima Adiati. Actually, I was not informed that the talk should be delivered in English. So I was a bit surprised, but that's okay. So it is my pleasure and my honor to be invited to give a talk and share knowledge to the physics communities of IPB University. So I'm very glad that the physics department already started bi-weekly seminar, or what you call physics talk. I guess this is a very good tradition to be held routinely at every scientific department, I would say, and to strengthen our academic atmosphere. So the topic I'm going to give in today's talk is about the topic that I have been doing pretty much since 4 years ago, perhaps. Although not really continuously, I've been doing this topic until about 4 years from then, right? But formally, until today, there is still even another paper that we are waiting for the review results at the nanomaterial journal for the topic that is still related to unconventional plasmons. So I have tried to make my presentation to be as pedagogical as possible. So there is a perhaps advantage of me trying to make my presentation to be rather pedagogical, which may be good, or which may, I hope, attract the attention of the audience better, because I will try not to talk too much of the abstract things. Rather, I would be talking about more simple and real things. But on the other hand, perhaps to those of you who may have been so familiar with the basic theory that I'm gonna cover again in this talk, I hope you won't be that bored with this kind of review of the basic knowledge about plasmons. So let me start with my presentation. Okay, can you already see the screen?
Not yet.
Not yet.
Okay. Oh, I haven't done the screen sharing though. Yeah, now I just did it. Okay.
Yes,
yeah. So I'm not sure about whether the look of the first page of my presentation pretty enough or not. So this kind of something that I don't have the good sense to say that this is beautiful, this looks beautiful or not. So what at least I assume more important is what appears in there looks clear to you. So the title is Unconventional Plasmons, Concept and Possible Applications. I am Muhammad Aziz Majidi from the Department of Physics of Universitas Indonesia. So here's the outline of my talk. First, I'm gonna review a bit about what plasmons are, and especially what is the conventional understanding of people nowadays about what plasmons are. And then I will go into more details about three kinds of plasmons conventionally understood by many people today. The first one is about plasmons. I'm gonna review about the basic model usually used to describe this kind of plasmons. Second, about surface plasmon polaritons. And then LSPR, or Localized Surface Plasmon Resonance. I'm gonna be talking also about the common theories that people usually use to describe this physics. Those are Rayleigh and me theories. Next, I'm gonna go into what is the core of this talk, that is the new kind of plasmons from the material which is among the family of strontium niobate oxide, where we discovered what we then call correlated plasmons. So this is a new kind of plasmon which has some natural differences as compared to what we usually understand as plasmons in conventional way. Then next, I'm gonna cover the previous theoretical attempts people have done in order to explain the actually other people and also our group, in order to explain the new kind of plasmons that we discovered in strontium niobate oxide. Then I'll continue with the theoretical attempt to further explain more rigorously about this new physics, and then continue with the results and discussion. Okay, first definition. So you all may have been familiar with the term plasma, which means a gas of positively and negatively charged particles of equal amount. So the well-known examples would be, we know that in the atmosphere we have the layer that is called ionosphere, which consists of the positive and negative ions. Both are moving around. And we also have something similar, but in the microscopic scale, that is what we know as electrons living in the environment of positively charged ionic background. So in this case, electrons are moving around, whereas the positively charged ionic backgrounds are static. Plasmon itself is the quantum term of the collective oscillation of the particles in the plasma. So as usual, as we have known from the term that has been used for defining photons as well as phonons. So now we know plasmon. So whenever we add the letter O and N after a word that comes from just classical physics, that usually means that if we want to treat the physics from the quantum mechanical point of view, they may be considered as particles. So plasmons, which are originally from oscillations of many particles, can be viewed quantum mechanically as kind of new particles, new particles with different characteristics or new characteristics. Okay, so conventionally, people have known that there are three kinds of plasmons. The first one is what we call bulk plasmon. By bulk, it means that it is contained in a three-dimensional material or three-dimensional container, if you would say, where the plasma can oscillate within this three-dimensional world. That's the first one. The second one is what we call surface plasmon. Typically, in order to have another kind of plasmon that can only propagate within a surface, we have to create a certain environment so that it can enable the plasmon to form and then propagate along that surface, and that surface happens to be usually the interface between dielectric and metallic materials. So that's the second one. And the third one is what has become rather famous, I guess, recently. That is the nano particles. I mean, plasmons in nanoparticles that we call localized surface plasmons. So by localized, definitely we mean something that doesn't really propagate over the space, but instead it only oscillates within the nanoscale container, that is the metallic nanoparticle. So this is just the basic concept of plasmons in general. So first I start with the the basic concept of bulk plasmon. So consider a bulk metal where we have electrons living in the background of positively charged ions. So if we shine some electromagnetic waves onto this metal, we can describe this electromagnetic wave as we can simply write the wave of the electric field without, basically we don't mean to ignore the magnetic field, only that the physics carried by the magnetic field is basically coupled with that carried by the electric field. So without explicitly showing the equations involving the magnetic fields, it is sufficient that we describe the full physics using only the electric fields. So consider that usually we use electromagnetic waves of the wavelength on the order of the infrared to UV wavelengths, which are all still much larger than the lattice spacing, lattice parameter. So this set up the good approximation for us to begin with. So using that, if we drive the electrons inside the metal using this wave, then consequently we can anticipate that the positions of the electrons with respect to their equilibrium positions can be represented by the position vector r, which has the same time dependence as that of the electric field. And then simply by applying Newton's law, Newton's equations of motion, where here we are considering that the electrons are exerted by electrostatic, not electrostatic, by electric fields, the time-dependent electric fields. And since the electrons are not alone, rather they are actually scattered by whatever obstacles that they have to face along the way they move around. So we have to add the second term, which is the dissipative term. Then by plugging in this time dependence of the electric field as well as the positions, we can come up with this expression. And then we can solve for the position vector. This gives us how R depends on E, or how R is related to the electric field. And then what is important here is that from the expression of R, we need to connect it to the quantity of polarization. So we can express polarization factor this way. Okay, then the reason why we need to express polarization as a function of the frequency is because we need to connect it to what we call correlation, dielectric functions, what we symbolize here with epsilon. So this epsilon is actually a complex number. So by substituting the expression of P into this relation, then this is what we get. Since epsilon is a complex number, it can be divided into its real and imaginary parts. So each of them looks as you see in here. So among the quantities involved in these two formulas, there is a quantity that we can extract that is called plasma frequency, which happens to be following this formula. So you will know better what plasma frequency is from the next page. So before we go on, first we need to consider a little bit corrections due to contribution of the other electrons. So what we previously already included in our model are basically only the free electrons. But since we still have some more electrons being tied to the nuclei of the ions, then we need to replace the bare vacuum permittivity, which is 1, with something that can have a value larger than 1, what we call epsilon 1 of infinity. So the corrected formula gives us the corrected formula of the plasma frequency like this. So before we go further, it is important for me to introduce to you what we define as the loss function. So the loss function is the minus of the imaginary part of 1 over epsilon. What does this really mean? So this actually means, so whenever we have electromagnetic interactions, we can always pay attention to the fact that there is some coupling, electromagnetic coupling, that is represented by 1 over permittivity. So 1 over permittivity value represents how charge and charge, or charge and electromagnetic wave, are coupled. So the stronger they are coupled, the stronger can be represented by this quantity 1 over epsilon. So in order to see in what circumstances or in what omega values this quantity become strongest, so we can, since 1 over epsilon is a complex quantity, so in order to get the magnitude, or maybe to be more precise, in order to get the poles of this quantity, it is easier if we extract it from the imaginary part, and we take the minus sign, because if we don't take the minus sign, then we will get negative values. So this is what comes up. So this is called loss function. The reason why it is called loss function, because it is related to how people may usually excite Bach plasmons using beam of fast electrons. So how much the energy of these electrons can decrease because of being absorbed by the material, is what is called loss function. So from the functions, the epsilon 1, the real part of the dielectric function, the imaginary part, and the loss function, we can gather all of them into one graph, and we can see the characteristic of several quantities. So omega p, what we call plasma frequency, turns out to be a measure of when the epsilon 1 becomes 0, the value becomes 0. And epsilon sub 1 infinity is some value that is achieved when omega is approaching infinity. So we can see that the loss function here shows a peak at the omega p value. So this means that LF can be a function that can signify the formation of plasmon, which is in this case Bach plasmon. Okay, so as we see from the curve, when omega is less than omega p, the epsilon 1 function has negative value. So what's the consequence of having this negative value? When epsilon, the real part of epsilon is negative, this implies that the wave vector of the wave becomes purely imaginary, because this is taken from the root of a negative value, which is imaginary. So if the k vector is imaginary, that means that the wave doesn't actually propagate, it decays. That is why if we shine electromagnetic wave onto a metal, if the frequency is in the range of from infrared to sometime somewhere before ultraviolet, the wave is usually reflected. So metal is usually a good conductor because of this characteristic. It can reflect almost perfectly. So another feature of having omega at the value of omega p is that epsilon 1 takes zero value. If epsilon 1 becomes zero, that means the displacement vector is zero, because displacement vector is epsilon times the electric field vector, right? So if D is zero, that means since the Maxwell equation, if we derive, we will see some relation that a double curl of E will be proportional to something times the displacement vector. So if the displacement vector is zero, that means curl E is zero. If curl E is zero, that means K cross E is zero. K is the propagation vector. If the propagation vector has zero cross product with respect to E, then that means the K is along the direction of E, which means that the motion is actually longitudinal. So we obtain here that the Bach plasmon is of longitudinal characteristics. So since it is longitudinal, then it cannot be excited by direct photon illumination, because photon has transverse characteristic in its propagation. So since electromagnetic wave is in free space is usually transverse, it cannot be used to directly excite Bach plasmon. So we can conclude that basically Bach plasmon almost has no use because it cannot be excited directly. But the knowledge of Bach plasmon is of course important because we can relate it anyway to the surface plasmons later on. Okay, before we talk about surface plasmons, we still can continue the discussion on the Bach plasmon by considering when omega is greater than omega p, then epsilon 1 value becomes greater than 0, which gives the real part of k becomes finite value, which allows transverse wave propagation. So only after omega becomes larger than omega p, we get back the wave. So that means if we shine a metal with electromagnetic waves having the frequency larger than the frequency, the plasma frequency, we can have the wave propagate inside the metal in this case. So usually the region above the plasma frequency of metal is usually already ultraviolet region, ultraviolet or higher frequencies. So if that wave can propagate, then the dispersion relation, that is the relation between the frequency and the wave vector, follows this relation. Okay, related to what I just mentioned about that the longitudinal plasmon cannot be excited directly by photon illumination, So then what should we do to probe it? So in order to probe Bark plasmon, not to utilize, so I'm not saying how to utilize Bark plasmon, but just to probe, just to sense it. So people usually use a beam of fast electrons. So we can bombard the some thin layer of a metal using a beam of electrons. Then we can measure how much the energy is lost from the electrons. So this is some typical graph of the experiment of, I think the experiment is called triple ELS or double E then, electron energy loss spectroscopy. Okay, next. The second kind of conventional plasmons, something that we call surface plasmon. Surface plasmon is another kind of plasmon that propagates on a surface or on an interface between two materials. The term polaritons means after the surface plasmon is coupled with photons. So if it is not yet coupled with photons, it is called surface plasmons. When it is already coupled with photons, then the combination between these two form something that is called polaritons. That's why overall we call it surface plasmon polaritons. So the physics of surface plasmon polaritons can be described by this kind of setup where we have two materials. Let's say one is dielectric material, the other one is metal, and between them we have a flat interface. So we want to confine a wave between these two media. So of course, if we have to do all the math starting from the Maxwell equations, it will take a long time. So I simply display here how the idea works. So so we want to have the wave being confined but propagate within the interface. So we can propose that the functional form of the electric field would follow this expression, where the propagation can be chosen to be along the x direction, and we may think of the amplitude to vary along the z direction, whereas along the y direction, from the symmetry we can guess that there is no dependence. So everything is constant along the y directions. So if we start from the Maxwell equations and we apply all the boundary conditions properly, eventually we can come up with the relation between the wave factor value of the propagated wave, which we call beta, which actually stands for kx. So we get the relation between kx and k naught. K naught in this case is the bare k that is associated with the k vector when the wave is still in the free space. Here epsilon 1 and epsilon 2 stand for the epsilon of each medium. So epsilon 1 is for the metal, epsilon 2 is for the dielectric. So in this case, epsilon 2 is considered just as constant value, real value, whereas the epsilon 1 is a complex function, which we can simplify the characteristic by assuming that the Dutt model works for this problem. So so if we work out this relation between beta and the other quantities, we can extract what we call omega SP, which is the surface. SP stands for surface plasmon. So omega SP stands for surface plasmon frequency, which is related to the bulk plasmon frequency or bulk plasma frequency divided by the square root of the sum of the relative permittivities of the two media. So, so this is the results. Further, we can draw the graph showing the how the frequency behaves as a function of the wave factor. So this is actually the curve that I'm showing using the pointer here, is the dispersion relation of the SPP, the surface plasmon polariton. So if we have the dielectric medium being just an air, so we have this curve. So if we replace the air with silica, for instance, then we have another curve with the surface plasmon frequency being less than that for the air. So here comes an important issue here. As surface plasmon polariton cannot be disconnected from bulk plasmon, essentially. So the omega SP, we have seen that the omega SP is related to omega P, right? So surface plasmon polariton has a close connection with the bulk plasmon, whereas bulk plasmon, we know it has the characteristic of having longitudinal behavior. So we can already anticipate that surface plasmon also has a problem of not being easily excitable by direct photon illuminations. So and that fact can be recast into some relation that is represented by the beta value, where the beta value becomes greater than the k naught value. So that creates a reason of why we cannot excite polaritons inside the interface between the dielectric and the metal simply by direct elimination of photons. So instead, we have to do something. We have to do some strategies. People, in experiment, the experimentalists or the people who do more applied research on plasmonics know better, of course, than I do about this. How to basically how to send the wave to enter into the interface between the dielectric and the metal in such a way that the direction of the K matches the requirement and also the magnitude. So both the magnitude and direction. So there are several means of doing so, and I'm only showing you two of them. The coupling through prism and another coupling through grating. Okay, so I have talked about two kinds of plasmons already, right? So now I'm going to be talking about the third one. The third one is about localized surface plasmons. Here, I'm just showing some ancient cups, Romans, 4th century Lycurgus cup. These two cups are actually the same cups, or there may be two cups, I don't know, but they are basically identical. So these two appearances, they are different only because one, the left one have the left one has a green appearance because we look at it where so we shine the light from outside, so we get actually the reflection. The reflection gives us green color impression to our eyes. Whereas on the right side, what we see is if the light source is put inside the cup itself. So when we are seeing it, so what we are sensing is actually the transmitted light, so not the reflected light. So that gives us different color, which actually reflects different majority of the wavelength of the transmitted light. So these all occur because of localized surface plasmons. So what's the physics behind this? So basically, the physics is simple in terms of the quantity that we deal with. Is basically only spheres, only metallic spheres, only that the size of the sphere is in nanoscale. So if the size is so small that it is within order of 1 unity or 10 of nanometers, that means it is too small, that typically much less than the wavelength. So the physics can be described by Rayleigh theory or Rayleigh scattering. So Rayleigh theory has been successful in explaining why the color of the sky is blue. Why we always see sky as blue. That is because of the Rayleigh scattering. The Rayleigh scattering says that, I mean, the results of the calculation derived from the Rayleigh theory tells us that the scattered intensity is dominated by lambda that is small, because the intensity is proportional to 1 over lambda to the 4. So, but that's another issue if we want to talk about Rayleigh theory in a more general way. But what we need to talk about using Rayleigh theory here is its relation with LSPR. Oh, by the way, the term LSPR, another word is added there, resonance, is when we achieve a condition where the frequency matches with the characteristic frequency of the localized surface plasmon. That should be D in here, localized surface plasmon. So the physics can be described using basically electrostatic, which means that what we need to solve is Laplace equations. We don't really need to apply time dependence as well as spatial dependence here, because of the condition that the sphere is so small that the variation of the electric field inside the sphere is negligible. So by solving the Laplace equation using the proper boundary condition, so what we obtain is the potential inside and outside of the sphere, and then from there we can conclude the expression of the induced dipole moment, which can then be also related to what we call polarizability. That is how good the metal nanoparticle can respond to the electric field to form the dipole moment. So apart from the possibly lengthy calculations, what usually people need to obtain are the scattering absorption coefficients, which if we add them up, what we get is what we call the extension coefficient. So the extension coefficient is something that serves similar to what we have defined before for the bulk plasmon. So as for the bulk plasmon, we have defined what we call loss function, right? So loss function is the function that characterizes whether we obtain plasmon or not. So in here, rather than loss function, we have the either scattering coefficient or extinction coefficient. So both can be used depending on how we measure the response of the lights shining into the nanoparticles. So if we only measure the scattering parts, then we may need to associate the intensity with the scattering coefficient. But if we integrate overall, so that we combine the scattering and the absorption, then we better use the extinction coefficient. Okay, so when we talk about the situation where the size of the nanoparticle being so small that that's much less than the wavelength, we can use Rayleigh theory. But if the size of the nanoparticle is not that small, rather it is comparable, the diameter, let's say the radius of the nanoparticle is of the same order or comparable with the wavelength, then Rayleigh theory breaks down, and we have to use another theory that is more advanced. That is called me theory. So me theory is basically a similar theory that has the same goal, that is to describe nanoparticles, but that is more with the validity that is wider. So I'm not going to discuss about how we derive me theory because it is pretty complicated, but basically the idea is similar. The only difference is that something that is usually neglected for the Rayleigh theory, we cannot neglect it anymore in the me theory, because when lambda is of the same order of the same order as the size of the nanoparticle, then we cannot neglect the variation of the wave inside the nanoparticle. So the theory has to be improved. So the improvement of the theory leads to much more steps to be done, so that I cannot explain in here, but I can only show the results, the different results obtained from the two theory. So if we calculate the scattering cross-section, that C scattering using both theories, then we see that the theory, the Rayleigh theory, doesn't seem to work well, because it cannot account for dependence of the size of the nanoparticles to give different peak positions of the scattering cross-section. So definitely me theory, it works better. So this is some experimental results. It turns out that if we work more rigorously on the calculations, all the coefficients, scattering, absorption, and extinction coefficients, all depend not only on the size of the nanoparticles, but also on the shapes. So this is an example showing that if we have three different shapes of similar size, it can give us different peak positions of the scattering cross-section. So there are numerous possible other ways to utilize LSPR. So LSPR typically are used to make waveguides. So as you know, waveguide is a device to guide wave so that we can make sure that the wave can reach the point we desire. Conventional waveguide, or the regular waveguide that we may have known, usually of some big scale, right? But using LSPR as a waveguide, it means that the waveguide is of nanoscale, because we need to make some device that can direct the light through something, which is, of course, on the scale of some electronic component size, right? So that device is called LSPR waveguide. I just meant waveguide in general, plasmonic waveguides, either using LSPR or SPP waveguide. So as for the LSPR, how can LSPR be used as waveguides? The trick is that we can form an ensemble of coupled change nanoparticles into forming into one 1D change, that so that they if they are equally spaced, they can form some lattice, and theoretically we can prove that they are coupled. By being coupled, they can form another feature, and this feature can be used and utilized as LSPR waveguides. Another way of utilizing LSPR is to form or to make what we call surface enhanced Raman spectroscopy, or SERS, where if you know how Raman spectroscopy works, basically this is just Raman spectroscopy. The function of Raman spectroscopy is the same, but usually Raman spectroscopy suffers from the fact that the signal is not so strong. To strengthen the signal, one may take advantage of the fact that if we put the sample, say the molecule or some analytes, in the region between nanoparticles, these nanoparticles can supply something that is called hotspot. Hotspot means actually the spot in which the near field generated by the dipole of the nanoparticles become combined between the nearby nanoparticles, giving the enhancement of the intensity for the Raman spectroscopy. So LSPR can also be readily excited by direct photon illumination, so that there is no need of phase matching. So this is the summary for bulk plasmons, surface plasmon, and localized surface plasmons. So now I want to start to introduce to you the issue why it is interesting that we have later what we call unconventional or correlated plasmons. So first of all, having known the superiority of plasmonics within the notion of photonics and electronics, where plasmonics can be considered as the realization of photonics for nanoscales. So it can serve the functionality of making the devices making the devices be able to handle photons within the nanoscales. So if we talk about photonics in general, of course, that means we talk about how photons can be manipulated. But if we only talk about photonics, that doesn't necessarily mean that we talk about nanoscale photonics. So nanoscale photonics so far cannot be realized until we have plasmonics. So plasmonics is the realization of nanoscale photonics. So, so that's the good thing about plasmonics. But what is not so good currently with plasmonics is because almost every materials that have been used for plasmonic application have suffered with the high loss. What does that mean? What do I mean by loss? By loss, it means, so essentially what we need to have is that we want to use plasmon as a kind of vehicle for the photons to be sent to somewhere as we desire through the waveguide, what we call plasmonic waveguide. So the plasmon is to be used as the vehicle. So who is the passenger? The passenger is the electromagnetic wave of the photon. So when photon rides the plasmons, we get the combination or the couple between the two that we call, if we deal with surface plasmon, we call it surface plasmon polaritons. So what we need is to have this surface plasmon polariton to survive from the start, from the starting point we couple the photon with the plasmon until it is the time for us to release it, right? So we don't want the plasmon to already decouple somewhere before it reaches the destination. Okay, so the need for making sure that the photon can be transferred into the destination without getting lost on the way. So that means we need to have long, what we call defacing time, long defacing time, which means the time scale that characterizes how long the photon can be kept by the plasmon, or the other way around. So if the defacing time is so short, then it is of no use. So the plasmon will not be able to work as we desire. So so we need to make sure that our polariton, surface plasmon polariton, will not lose much of energy, or will not lose its connection with plasmons. So this thing is simply measured by the quantity of the imaginary part of the dielectric function, the epsilon double prime or epsilon 2, as I used the symbol before. So as a matter of fact, even noble metals, typical noble metals, still have the values of loss, or the values of epsilon 2 being some high value, like in this in this example. For instance, the black curve, that black curve is for K. K is potassium, right? So the peak is of the order of 4. 4 is actually a big value. Why I would say that even 4 is already a big value, because it turns out that with using the unconventional plasmons that we later on discovered, we could get plasmon that can have the loss value as low as below 1, as we can see, we will see later. So this is the new thing that I want to introduce, the strontium niobium oxide, SRNBO III family. So maybe I don't really need to talk about too much details of the crystal structure. So, but what is important is that, so at some x values, so if we have, so this kind of compound can be controlled how much it can contain oxygen by some experimental means. I'm not an experimentalist, so I don't know exactly how we do it, but experimentalists can say that they can control the oxygen content. So when we give excess of oxygen, it turns out that the excess of oxygen can stay and make some patterns in a way that they form walls. So they form walls in the materials, being equally spaced between the walls. Like for instance, here, so this EOP, I don't remember what I wrote it, but so this EOP anyway, this is the excess of oxygen, excess of oxygen, sorry, that resides forming some walls in here, So what do these walls do to the material? It turns out that they separate between section on the left and on the right of it, making the electrons confined between the two walls. So that is the special thing about this material. So using that, I mean, by controlling the amount of oxygen contained in the material, it turns out that we can control the optical properties of this SRNBO materials. So as you can see here, our colleagues, the experimentalists, have synthesized three samples. One is called LP. LP means light. I think LP means light pressure, something like that. M stands for medium and H stands for heavy. So that characterizes the amount of oxygen content. So when we have only little excess of oxygen, we see the characteristic of the epsilon 1. It follows the regular metal character. That's the epsilon 1. So the bright red and the dark red basically follow similar trend. That is the Drude trend, the trend for the regular metal. But if we see the blue one has a different characteristic. It is kind of flat, and all the values are above the zero value. So it means that within this 0 to 6 or so EV, the value of epsilon 1 stays positive. So that means that it is not the characteristic of regular metal anymore. So although they are from the same parent compound, but having been controlled with different excess of oxygen, we can tune at least one among the three samples to become no longer metallic. So the heavy, the HP sample becomes no longer metallic, although the other two are still metallic. So if we now look at the epsilon 2, value and the loss function. So this is the epsilon 2 for the light, for the smaller content of oxygen, so it still behaves like a regular metal. But for the here the green one is the curve for the loss function, which also still shows regular metallic character for the LF. The blue one is the middle one, still the same. So these two are still showing a metallic characteristic, although they already have different content of oxygens, but the amount of oxygen are not yet exceeding some value that turn the characteristic completely. But when we look at the HP, I mean the sample with a heavier level of oxygen excess, the characteristic of the epsilon 2 becomes completely different. See, if you compare between this curve and this curve, they are completely different. So what is interesting is that here for the heavy pressurized with oxygens, the curves of epsilon 2 and the loss function become so similar. I mean, they are showing peaks of the positions that are pretty much the same. So there are several features that I can underline here. First of all, if we look at the regular metal loss function characteristic, it always only shows a single peak that corresponds to omega p, bulk plasmon, right? But here, what we see that there are 3 peaks. At least here there are 3 peaks. These other wiggly structures, as we have investigated, they are not related to plasmon. So we only need to consider these 3. So these 3 plasmonic peaks, we can still claim that they are plasmons, but they are of new kind of plasmon. They are no longer the same as the conventional ones. They are not the same because, in fact, the LF function almost coincides with the epsilon 2 function, which are completely different characteristics compared to the regular metal. For the regular metal, see, this is epsilon 2, this is LF function. They are completely different. But here they are coincident. And they also have more than 1 peaks. So there are more peaks. In this case, there are 3 peaks, and epsilon 2 and LF functions are coincident. So these are some features that the new kind of plasmon has. So the question is now, how to explain it? So when we publish this paper, along with the report of the experimental data, we also have attempted to do the explanation using some simple model. So this is actually the theoretical calculation results, which so if you just look at them at a glance, our model seems to work very well, right? So this is for the less exposed to oxygens. This is for the sample for the heavier exposed with oxygen. So they are, so the result seems to reproduce the trend of the experimental data very well, which looks like this, right? Look like this. This one look like this, okay? And this one look exactly like this. I mean the trend, of course, not in every detail. So before we, okay, this is actually part of the paper itself. So along with the experimental data, we also supply with the theoretical calculation based on some simple model, classical model. Well, maybe a year after that, another paper tried to produce some calculations using P means, which gives these results. Probably I'm not going to address that much of this work. So what I wanna try to tell you what is important is how do we actually obtain these results. So the way you obtain the results actually is quite simple. First, since we want to jump to some picture that can directly bring us to closer to how we can interpret the experimental data. So we start by assuming that, so we of course we have to start with some hypothesis. Within our hypothesis, so we think that the electrons are confined because of the two walls. How many electrons are confined, we don't know yet. So this is something that we want to vary to the number of confined electrons. But let's say that we have a few electrons connected with some potentials that are represented by some springs in here of different spring constants. Also, initially, I put equal magnitude of charge as well as the sign, but later on, the need for matching the results with the experimental data requires us to, turns out that we have to alter the sign of the charge. So positive, negative, and so on. So basically what we do is simply kind of like root model, but of course modified to certain setup like this. So what is important is that in doing so, we are forced by how we want to make our result agree with the experimental data, that the mass of the electrons needs to be multiplied by some enhancement factor, which is about 25. So we can interpret here that due to the confinement and correlation effects, the inertia of the electrons become 25 times heavier compared to the bare electrons. And interestingly also, that the sign of the charges become no longer just minus, but they have to be put in a way that they are alternating. So plus, minus, which then we can interpret that they actually form not just electron, but electron, hole, and so on. So that is the interpretation that we make, that using this as a model, we succeeded to finally reproduce these results. So later on, of course, that gives us some homework as to how we could explain this using the bottom-up approach. I mean, using the more microscopic point of view. That is something that we have done later. So this is the next work that we did in order to explain or to give theoretical verification of why we claim that the electrons have been renormalized heavily like that. So we start from the quantum mechanical starting point, that is by proposing our Hamiltonian. So our Hamiltonian, our quantum mechanical Hamiltonian is based on tight binding, tight binding plus interactions of Hubbard type. So we call this generalized Hubbard model. So using this general Hubbard model, so what we consider in our model is that, so we have, this is the part that gets separated by the oxygen walls. So these are the oxygen walls. So these are the atomic sites, but at each atomic site, we can consider that there is one charge that is to be entered into our Hubbard model. So our Hubbard model will contain either 3, 5, 7, and so on, number of sites. But we still consider the model as simple as possible. That is, we start with just one-dimensional model. Actually, the reason why we did one-dimensional model is because if we do a higher dimensional, if we are doing a higher dimensional problem, then it requires way bigger Hilbert space, quantum mechanically. So that is much more difficult to handle because that would require a bigger computational resource. So fortunately, we kind of have the physical ground on claiming why we can just use one-dimensional model, because even the experimental measurement has indicated that the transport of the material shows that one-dimensional characteristic. So, so this is the details of why, starting from laying out the Hubbard model, then we proceed further several steps within the many-body theory technique. So basically, what we do is we set up the basis, the end. So if we start with n atomic sites and n atoms, or maybe less than n atoms, so we may start with, let's say, 5 atoms with only 3 charges. Then we can count how many configurations that we can have within this 5 and 3 number of sites and number of electrons. So basically we can, we end up with a big number. So starting from 5 and 3, we should end up eventually with a big number, because the number will follow combinatorial relation. So there is some factorial, something like that. So so without, I think, spending too much time into these details, so basically what we need to do is to set up our Hilbert space within so basically what we do is to set up an exact way of solving finite size problem. So the problem is of finite size, actually small size, but the Hilbert space that we have to set up becomes big because it goes through some combinatorial relation, right? So this is just part of how we have to do the process of diagonalizing our Hamiltonian within this n particle Hilbert space, which eventually the almost ending step that we have to do is to define the Green function from the results of the exact diagonalization. So from the spectrum that we obtain using the exact diagonalization, we define the Green function, or we construct the Green function. So what we construct, the Green function that we construct here may contain some thermodynamic effect that is contained in the beta here. Beta is the 1 over constanta Boltzmann constant times temperature. And then we can continue with the definition of spectral function, the density of state, and so on. And then we can continue with the calculation of optical conductivity using linear response theory, the Kubo formula. And finally, we can calculate the loss function, something that we can eventually compare with the experimental data. So let me skip this part because these are not the most important part. So I guess what I want to show here, the most important one is, so this is the pattern that we obtain using our classical picture, but now we obtain it again using more rigorous quantum mechanical approach. which justifies what we have done within the simple model classically. And remarkably, not only that we have been able to show the exact trend of the epsilon1, epsilon2, and the LF function, we can also, by some interpretation, we can also show that it is true that the charge are distributed alternatingly like this, alternatingly. So there is a side that has almost empty charge. So supposing that this consider that that we have a system of 5 sides. So the two end sides are having very little amount of particle. The probability of finding the particle very low, almost 0. And this one is almost 1. This is almost 0, but not quite 0. So this is kind of like behaving like hole, electron, hole again, almost, electron again, hole again. So that is what we call renormalization. So what is amazing here is that we can always begin with homogeneous electrons, but when the system becomes correlated, the behavior becomes surprisingly different from the picture we start with. Like for instance, in here, we have alternating electron pattern. Electron, like in hole, electron, hole, electron, hole, electron, like that. So we claim that we have been able to explain what we obtain experimentally. Unfortunately, this work has only been published in Proceeding because the time for myself to finish the paper to get it published in the journal is kind of it's so expensive to have that time, so we haven't actually managed to write our results for publication in journal, but I guess I have to do it soon. But these are in some way already published in Proceeding. So these are actually the reproduction of the model to explain the behavior of the system when the system is still showing the metallic behavior. Okay, last, I want to only briefly cover our recent work, theoretical work using DFT. So basically, the main goal is to test. So we previously already claimed that in systems where we have strong interactions, then we can have strong correlations, and this correlation will lead to formation of correlated plasmons. And now the question is, if you want to do this for some typical correlated materials, like cuprates, where, as we know, cuprates, many cuprates materials, in the cuprate family, can have superconducting phase. Right? So the superconducting phase is also a result of correlation effects, magnetisms also, and many other exotic features of cuprates come from the strong correlations, due to the strong interaction. So we want to know basically whether the theoretical framework that has been established so far, such as DFT, can be used or can be reliable enough to capture correlative plasmons. And so this is our publication in Rapid Communication of Physical Review B, in collaboration with the group of NUS. So, oh, hold on. Actually, I messed up the page. Yeah. continuing this one, actually, this should be this one. Okay. So the results of our study, our DFT study, did show that our calculation capture correlated plasmons. Why do we claim so? It is because we can see that the characteristic of epsilon 1 is not like metallic behavior. So this is no longer metallic behavior. And also here, if you see, this is epsilon 2, this is loss function. And epsilon 2 and loss function, look that they are almost coincident. I mean, the location of the peaks are almost the same. They are not quite the same, but almost. At least they look completely different from the conventional metal picture. So as we know, cuprates, when we can tune by some way the local Coulomb interactions to be as weak as possible, then the system will turn out into a metal. But if we can control it in such a way that it becomes stronger, then it will open a gap and the system becomes an insulator. So this is really captured. So I want to comment here the fact that the DFT can capture correlative plasmons. It is rather surprising because usually DFT is assumed to be insufficient to capture exotic properties of strongly correlated systems due to the drawback, due to the lack of how exchange correlation functional from the consham functional. So that is because only the weak part of DFT. But as long as so that is still believed so. That is still the benchmark of the DFT, that the DFT cannot be used to naturally capture metal to insulated transition. But it turns out that if our goal is not really to show the complete characteristic of strong correlations, rather, if we want to see only the formation of the unconventional plasmons, the algorithm turns out to be already sufficient. So basically, that's the conclusion. Yep. And the other conclusions are basically more basics. We know after this study, we become more aware that the formation of the plasmons is the origin is dominated by the hybridization between the orbitals, the p orbitals of La and the d orbitals of the copper. Other things, there is a competition between the U and the hybridization. So if we control these two, if we can control these two parameters, we may change the characteristic of the plasmons. Yeah. This is what I mean by the last page, actually. So, as I promised from the title that I want to address possible applications of these correlated plasmons, of course, I don't mean that I already have in hand the exact recipe of how I can utilize the correlated plasmons to develop plasmonic devices. But I can only at least provide the ideas. So to think of possible applications of correlated plasmons, we may like to take advantage of the fact that the correlated plasmons have significantly lower loss as compared to most noble bulk metals. And the correlated plasmons are readily excitable by direct photon illumination, so that no phase matching or mode matching strategy is needed. So having these two aspects in mind, thus some of these ideas may worth studying experimentally. I'm not saying that I'm giving you a recipe that you can just take and then apply it and you can get the device. No, just do research based on these ideas. To devise a plasmonic waveguide using one of the SRNBO family materials, where the correlated plasmon formation may be controlled by adjusting the thickness or extra oxygen content. The potential advantages of such a device lies in the selectiveness of the plasmon frequency and the unnecessity of phase matching process. So the difficulty in trying to find out how to do the phase matching is no longer needed. So that is the good advantage, the big advantage. And last is to develop localized surface plasmon resonance devices using selective plasmon frequency values and having longer defacing time as since it has low loss. So, and this is the end of my talk. Thank you very much. I apologize if I have exceeded the time. So I'm returning the time to the MC. Thank you.
Yeah, thank you very much, Dr. Aziz, for the amazing presentation. So we have a few minutes for the Q&A session. So for the participants who wants to ask the question directly, you can just turn on the microphone.
I have two questions.
Yes.
I have
I
to
already
take
get the question
prior.
from the experts.
Okay. First of all, Pak Aziz, you have a very nice presentation, and I really like your presentation. The physics is astonishing. I have two questions, Pak Aziz. The first one is you say that the correlated plasmons have low loss in the optical regime. Maybe you can give some elaboration on this, because this is interesting. Yeah, you said it's because of the oxygen atoms localized in this system. My second question is, in the Hubbard model, you consider the one-dimensional system, right?
Yes.
The one-dimensional oscillator. I am curious if you, in the future, use a two-dimensional model, because I see the structure can be analyzed also two-dimensional, and I think there might be some, besides longitudinal, also transverse mode, right? If we have two-dimensional model. So maybe this additional feature of two-dimensional can, in the future, better model the system. What is your idea about this? Okay, this is my two question. Thank you, Burima.
Yeah, thank you very much.
Yes.
Interesting questions. Can I answer directly?
Yes, you may.
Ibu Rima, yeah. The first questions is on the low loss aspect of the material, right? Well, first of all, I think to be safe, to give you the answer that is guaranteed by the experimental fact. So that is what we obtain from experiment. So in fact, the epsilon2 value are so low as compared to at least noble metals like gold. Gold may have like 2, 4, whereas this material only has 0 point something, 0 points. I don't remember. It is like 1/6 of gold. So that is from the experimental data. But from the, unfortunately, although I have actually calculated the loss function, I myself haven't really paid attention on what value actually we have got. So we should actually be able to verify whether our model can also capture why maybe I can show it from okay, if I
Hello.
Yes.
Is it possible to use DFT to investigate such problem?
At the end of my talk, I actually showed our more recent study that is in fact using DFT. So it depends on the goal. If the goal is just to obtain some physical insight, not to really obtained quantities, numerical quantities that are to be directly compared to the experimental data. If that is the goal, if our goal is to really compare the results to the experimental data, maybe DFT can still be assumed not good enough to do that job. But just to get the physical insight, such as just to show whether we can really get the trend where epsilon 2 and loss function can have coincidental frequency, characteristic frequency positions, that is sufficient. So that DFT is sufficient. So I was going to answer your previous second question, but in order to do so, I actually have to look at my results for the epsilon 2 value from my Hubbard model. So I may give you probably later, and not to take too much time. I only need to look at my data and tell you whether our model can really capture already not just the trend but also the magnitude. So I guess at the moment that's my answer.
Yes. Thank you. Was the answer satisfactory, Mr. Hendrati?
Actually, it is shown though. It is shown here.
Yeah.
Pak Dodi. So
Yes,
if you look at the blue curve here, see that is showing our epsilon 2 characteristic. So at least, although our results do not show the too low values that experimental data have actually shown, but at least the values that we obtained are of much lower values compared to the values of noble metal. So this is actually 1. The maximum value of epsilon 2 that we got is 1. So the two other peaks are less than 1. Yeah. So at least the trend looks
is nice.
Yeah, it's going to the correct trend.
Yeah, my question is that there is possibly also the transverse mode, not only the longitudinal plasmon oscillation.
With regard to your last question on whether it is better to try to do two-dimensional model. Of course, I would agree with you that of course to be able to model more realistic system. I mean, the system that is more realistic, that is that resembles more to the real system, that should be better, of course, but it will come with obvious challenge, that is the use of computational resource that will increase very significantly. So I guess
the problem is always with computational.
Right. I would say at the moment we anticipate that it is far from sufficient that we will be able to develop the algorithm for the two-dimensional system using the method of exact diagonalization. It is, I think it is well known that exact diagonalization is always usually used for finite and small size system. So if the system is already rather big, then the Hilbert cells become very big.
Yeah.
So
that's the problem, is in the matrix diagonalization you will have a
exactly.
Thank you, Pak Aziz. Thank you very much.
Yeah.
Okay. Next, we have question from the chat from Sophie Oktari. The first question is, when we consider conventional plasmon, the bulk plasmon is longitudinal because the epsilon 1 is 0. What about the unconventional plasmon? The epsilon 1 is not 0.
Yeah.
The answer is yes.
The answer is yes. That is actually the main fact that distinguishes the unconventional plasmon with the conventional one. But why are they still called plasmons if the plasmon frequency doesn't coincide with the 0 of epsilon 1? So that may be your question. I don't know. So if you think that the definition of plasmon is something that if you want to define the frequency characteristic, it has to be associated with epsilon 1 being 0, then I don't agree. So epsilon 1 being 0 is I think it is just an accidental fact that corresponds to the bulk plasmon. What I mean coincidental is because the more proper way to define plasmons is by looking at the loss function. As I said earlier, why loss function should be the more appropriate quantity to define a plasmon? It is because it is actually counting the poles of the 1 over epsilon, whereas 1 over epsilon is actually measuring the characteristic of the coupling between entities that we couple using electromagnetic interaction. So that's what defines plasmon. So if plasmon simply defined by loss function, or similarly for the nanoparticle, it is defined by something that is in there in the formula of the C extinction or C absorption. They are the same. They serve the same purpose. That is to show the characteristic frequency of the plasmon. So having the fact that epsilon 1 being 0 for the bulk plasmon, that corresponds to having longitudinal mode, which turns out to be different from what we later obtain in the unconventional plasmons. That's actually the interesting finding, because now we have another kind of plasmon with non-longitudinal mode. I mean, plasmon that can be excited directly by illuminating photon without necessarily having to do any phase matching. I hope that answers the question.
Okay, the second question is unconventional plasmon a propagating plasmon or localized plasmon?
Can be both. As well, similar to conventional plasmon that can be viewed in the bulk or in the nanoparticle. So we can also make correlated material to be nanoparticle, or at least we can make the nanomaterial, we can make the strongly correlated materials to be of thin film forms, for instance. If we make the strongly correlated material to be of the form of thin, very thin layer, that means we are confining the material, right? So when we are confining, that means we already impose some confinement effect without really doing anything with the material. So that is also another aspect that we may like to study. So localized or not localized, it depends on the physical size and shape of the material. So that's my answer.
Yes,
Bu Rima.
Thank you. Yes.
Mr. Yan Pandu rose his hand.
Yes.
Maybe he wants to ask something.
Okay, go ahead, Mr. Yan Pandu.
Okay, thank you for the presentation, Dr. Aziz. My name is Yan. I'm from Institut Teknologi Bandung. First, I would like to maybe confirm first about the condition or the signature of this unconventional plasmon. Is it when the epsilon 1 shows no negative or maybe less negative, or when the peak of loss function is not coincide with the position of epsilon1 equal 0. That's my the first one. The second one is how about the scattering rate? Because in Drude parameter we have a scattering rate, and the condition when plasma frequency W omega p epsilon1 equals 0 is only hold when gamma is very small compared to the plasma frequency. So how about the scattering rate in Drude in the case of unconventional plasmon? Thank you.
Okay, I hope I won't forget the questions. So the first one is about
the signature of the conventional plasmon.
Signature or how we may precisely define the
yes, correct,
the unconventional plasmon with respect to conventional ones, right?
Mm-hmm.
So I would say there is no rigid definition as far as this kind of issue has not been something established, followed by many people, in physics at least. At least only maybe a few groups in the world have really paid attention on how we define it. So the way we define it, of course, is not something that that has to be absolute. So, but I would say to make things simpler, to define something unconventional, usually whenever we observe the deviation from the original definition of the conventional one. So the original definition of the conventional one, at least if we consider bulk plasmon, is the coincidence of the zero crossing and the loss function. Yes. The peak of the long function coincides with the zero of epsilon1. So that's what we have understood as conventional one. Okay. When this criterion breaks, then it becomes no longer conventional. Okay. So that's the easy way. So at least what we have observed from what we call correlated plasmons, the characteristic of epsilon1 is no longer behaving as regular metal, because in fact the correlated plasmon that we mean turns out to be already in insulating phase, actually mott insulating, mott-like to be more precise. Mott-like insulating phase is no longer a metal. That is why it doesn't follow the metallic trend. That is why it is staying up at the positive value for the epsilon1. That is why it never has zero, because it is all the way on the top of the zero line. So, at least having one characteristic violated from the conventional definition, that already defines the unconventional. So, okay. Yes. I don't remember the second one.
The second one is about the scattering parameter.
Oh, scattering parameter.
Yeah.
Yeah. Well, actually, the scattering rate or the gamma or the 1/tau quantity, right, in the Drude model, it is essentially something that has no longer been considered when we consider correlated materials. So whenever we start considering to solve problems of correlated materials, we already leave Drude model, because if it turns out that our results can have similarity with the Drude trend, that is another issue. But the way we start is not Drude model. Like, for instance, the way I solved the problem that's actually to address the metallic phase of the SRNBO, right? Yep. The one that corresponds to the lower exposed oxygens. So that our result can show metallic behavior, but we didn't start from Drude model. We start from Hubbard model. No. Well, there is no tau in there. Let's see. Yeah. Right.
Correct. Okay. Thank you.
I hope that answers the question.
Thank you. Thank you, Professor Husin.
Thank you, Mr. Yan.
Thank you for the answers. This might be the last question. in the chat from Adam Badra. Can we include Lorentz force in the plasmon equation of motion? It may be important for systems with strong spin-orbit interactions.
Of course we could. Of course we could, but we need to work out, the calculations to see what comes up. And I haven't done so. So that's my answer.
Purima, may I ask question?
Of course, we still have the time.
Oh yeah, thank you very much. Thank you for Aziz for coming to this IPB physics talk. This is kind of nostalgic for me because I used to work maybe a little bit similar because I look at the plasmon formation. Yeah, you saw me that some peaks. So that's actually I did maybe almost the same, but in other system in atomic nuclei. Yeah, but still we were talking about the mesoscopic system, right? And the formation of the plasmon, it's kind of similar with the pairing formation, where we have a collective phenomena. So this is the collective effect. So when we have a infinite number of states and they interact with each other, so we will have one particular states that make by itself, and this is like a pairing, or in your case like a plasmon. And regarding the the application of the surface plasmon resonance. So for example, right now people try to use photodynamic, something like that, photodynamic or phototherapy. So actually using a particular material like graphene or graphene oxide, where this material could absorb a particular, for example, actually right now I'm working, but still in a preliminary stage. The spike glycoprotein actually can be absorbed by the graphene, and we can use the graphene surface, graphene oxide surface, as a hotbed. So once the virus trapped, so we can use the illumination, yeah, like you said. And actually I read some paper regarding the using of fast laser, and they did the calculation. They got like the temperature, the local temperature on a particular site, on a local site of the surface could reach until 50 or 100 degrees Celsius. And actually I did some simple calculation, but still maybe just get the half. So maybe in the future we can collaborate, try to make the model more perfect. So that's all. And also for the what is that? Now I forgot. Okay, I think that's all. I forgot. So that just comment maybe, yeah.
Well, thank you very much, Pak Tony. And in fact, the reason why I'm very happy being invited to share my knowledge, my experience, at least for this particular issue, not to just fulfill, so that you have this first round physics talk program, but also, of course, if from my talk I can get among the audience some interest to know more, and then maybe to be willing to share also, which end up, we can look into possible collaboration. That would be very nice for me. So of course I would welcome to have collaborations between the IPB and UI group. So and of course, so whatever we have known something that I don't know yet, and vice versa. We can complement each other. So I thank you very much for the invitation for collaboration. Thank you.
Thank you very much for the answer, Dr. Aziz. And for maybe that's all for the Q&A session. For the next agenda, I would like to invite Prof. Husin to give a little concluding remarks and maybe token of appreciation for our speaker today. Time is yours, Prof. Husin.
Okay, thank you very much, Bu Rima. And thank you very much for Pak Aziz for your very enlightening presentations to us. Yeah, this is the first time physics department to help to organize this kind of event. So this is very wonderful for me. And also I would like to take this opportunity to ask you one very last question. Yeah, because I haven't get opportunity. So I wondered, what is the meaning of hole in your classical model? If I'm not mistaken, I heard that you mentioned that your classical model interpreted as a hole. For a quantum mechanical models, then to interpret a hole is quite easy because it related to a vacuum state, probably. Thank you.
Yeah, well, I think solid state physics, when we start saying that we are doing something within the classical level, it may not be quite true that we are completely only doing classical without ever touching quantum mechanical paradigm. So I don't believe that we can completely free of not involving ourselves into we can keep staying away from quantum mechanical effect. So it turns out that when we talk about classical picture, what we mean is actually classical with respect to the established knowledge of solid state physics, which already contains quantum mechanics. Okay. So basically, whenever we talk about electrons and holes within root models, within DFT, by no means it is disconnected from quantum mechanics. It is always connected. Only that when we talk about treating the model quantum mechanically, fully quantum mechanically, means that I think we should, in this case, we are just being more consistent in accommodating the quantum mechanical requirements. So there's nothing, so as much as we can, we try not to avoid every quantum mechanical aspect that we have to satisfy. So I guess that's the answer. Okay. At least my subjective answer.
So thank you very much, Aziz. So I would like to give from our department a token of appreciations. This is a certificate of appreciations for you. Thank you very much. And I hope, as Pak Tony said, that we would like to establish collaborations between your research group in University of Indonesia and our divisions in theoretical physics at IPB. So I hope this will be something to happen in near future. And so again, thank you also very much to the all participants for participating in this first physics talk, and hope that you will be able to join again in our next physics talk with a different with different topics, certainly. So that's it. I will deliver back to Bu Rima. Thank you, Bu Rima.
Thank you very much, Prof. Husin. So everyone, that's all for our agenda today.
I thank you very much also to the organizer of this event, to Professor Husin, Dr. Dodi Hendradi, Dr. Tony Ibnu Sumariada, and Bu Rima, yourself, for the nice work for moderating this. And I welcome very happily your invitation for having collaboration between us. Thank you very much.
Thank you very much, everyone, for joining us this afternoon. We hope that all of you can join.
We need to take picture.
Rest of your week. Oh yes, of course.
Don't forget.
Okay. If all participants can turn on the cameras, please. Okay. How about the rest? Okay. 3, 2, 1. Okay. Thank you very much for joining us in the first Physics Talk 2021. Hopefully we meet again in 2 weeks' time with a different topic. So my name is Rima and thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.
Terima kasih Pak Aziz ya. Ya, jangan bosan-bosan.
Terima kasih undangannya, terima kasih undangan kolaborasinya.
Ya.
Mohon izin live ya.
Ya.